right. So last section of chapter P is inverse functions. Inverse functions is stuff y'all have done before, and we have those objectives. Inverse function. So we know that an ordered pair can represent a function. We've seen that. A function's just any relationships that connects an x value in the domain to a y value in the range. That's what a function is. So we know an ordered pair can represent a function. For instance, f of x equals f plus 4. So we can say the set 1, 2, 3, 4 corresponds to the set 5, 6, 7, 8. F of x plus 4 we can say is this here. Now there's more to the function than just those 5 ordered pairs. There's an infinite amount. It's a straight line. In this case, by interchanging the first and second coordinates of each function, we find the inverse. And really what this is saying is probably going to say it here in a minute. We bring out 2 circles. This here we can say is the function f of x. It's taking the point 1 and connecting it to the point 5. An inverse function will take the 5 from the range and connect it back to the 1 in the domain. An inverse is just going from the range to back to the domain. The function takes a point from the domain and connects it to the range. The inverse takes the range back to the domain. And we have this here. So it works out that f inverse of this here is going to be x minus 4. And has the effect of undoing each other. One undoes the other. And if we take the composite of the function and its inverse, we get back to x. So we could say f of f inverse of x is equal to f inverse of f of x, which both equal x. Or really what this is also telling us is that 2 inverse functions are reflected across the line y equals x, our linear function. Figure that out. So we had x plus 4, x minus 4, x. So we have this here. So they're reflected across that line. The distance from the blue equation to the purple and the purple to the red are going to be the exact same. They're reflected across this line. And that really makes them inverses of each other. So find the inverse of f of x equals 4x. So if we want to find inverse, there's several main steps. First is to rewrite f of x as y. Now, if we already have the equation as y equals, we don't have to do this step. It's already done for us. But here, we can rewrite it as y equals 4x. Second step, switch x and y. Now, this is not talking about any kind of operation steps. We're just literally going to switch x and y. We're switching the spots. Because the function, as I've said, or kind of we've seen already, is taking a domain value to the range. Its inverse is taking a range to the domain. We're really switching the x and y, the domain and range. And that's why we do this here. Step 3 is now to solve for y. Solve for the y value. And for this one here, it's actually not that bad. We just divide both sides by 4, telling us y is equal to x divided by 4. And the last step is to replace y with f inverse of x. And as an anecdote, w with a slash is with. If you put an O after the slash, you all know what that is? Without. With and without. So, lastly, f inverse of x is x over 4. That's it. Questions on this here? Now, we can look at the graph, clear that out. 4x. That was our original function. So we have this here. So we know that its inverse should be kind of coming above the purple line and then below. And we do have exactly that. They are reflected across this line. Questions on this here? If we look back at this previous slide, so then verify both, give us the identity function, we can do that. So this, we found it. Now if I want to verify it, what we're doing is f of f inverse of x. Now f inverse of x we have right here, x over 4. And taking f of x over 4 is we're plugging it back into f of x, which means we have 4 times x over 4. We replace every x in the function with x over 4. We're used to doing this with our composite functions, yes? And our 4 times x over 4 is indeed x. Yeah, 1x. We can do the same thing with f inverse of f of x. Well, f of x is 4x. And if we replace every x in our inverse function, we'd have 4x over 4, which is just both give us x, so we're good there. Any questions on any of this here? Okay. And for the most part, finding inverses, especially in Algebra 2, were not too complicated. There wasn't a whole lot to it. I say that for certain, especially with our linear equations. They're not too bad. There's not too much involved. And to prove that two functions are inverses, we just take our composites. F of g of x and g of f of x. And if they both give us x, they both give us the same thing, then they are indeed inverses. But if one of them does not equal x, we can stop there. Because if one of them does not equal x, 1x, it is not an inverse. It doesn't matter if it comes out to be 3x, that's still not x, it is not an inverse and we can stop. Because again, for this to be true, both of these statements have to equal x. It's not one or the other, it's both. And because it's both, as soon as one of them doesn't, we don't have to check the other. We don't have to check the rest. Does that make sense? We can know immediately that it's off and we can move on for proving or disproving that they are inverses. Do not be confused by the -1. It's just saying it's an inverse. That's all the -1, f to the -1. We've talked about graphs of this here. It's reflected across that line. Now, to be able to tell graphically if a function is going to have an inverse is the horizontal line test. Horizontal line test. Because if we're talking about a function to exist, if it is a function, let's go back to that. How did we denote a function? Was the vertical line test, straight up and down, yes? If it crosses that line more than once, it's not a function. Well, we use a horizontal line test to see if its inverse is a function. Because what are we doing to find the inverse? We're switching the domain and range. We're switching those two, yes? So if a line crosses the range, y values at more than one point, that's fine for a function. Quadratics, U-shaped graph. This is indeed a function, yes? Now it doesn't pass the horizontal line test because there are spots where we have two different y values, or the same y value with two different x's, which is fine. For a function, that's fine. But if I'm switching the domain and range, that single y value that crosses at two spots is now the domain, which means I now have one x for two different y's. Does that make sense? Because we're taking this and flipping it to be this, which now this function here fails the vertical line test and doesn't work. And this is why the horizontal line test works, because of that flip from the domain to range. And that's how we can test to see if a function has an inverse. Or more specifically, not that it has an inverse, that its inverse is a function. Can it still have an inverse? Yes. Because can we still have equations that are not functions? Well, yes. Biggest case in point is a circle. Circle has an equation. It is not a function, but it still has an equation. So that means even quadratics have an inverse, but their inverse is not a function unless we restrict it. We put restrictions on the domain of the original function so that it does have one. This is a one-to-one function. A function is one-to-one when each value of the dependent variable corresponds to exactly one value of the independent. 1x to 1y. So a quadratic is not considered one-to-one because we have 2 x's, 1y, not one-to-one. And we can look at it here because we can see, then they highlighted it in red. We have two different x values, or that's the inverse, because here we have two different x values for the same y. And when they flipped it, found its inverse, we now have 1x to do different y values. It doesn't work. Or at least it's not considered a function. It still has an inverse. The inverse for this function would be plus or minus the square root of x. Still a function, or still has an equation. There is an inverse, but its inverse is not a function. So normally what we'll say, especially in these cases, is that x has to be greater than or equal to 0. We're talking about only the positive side, which means its inverse is a function. It's just that it's restricted to the positive square root of x. That's all we have to do. We have to take one or the other if we want it to stay a function. Which gives us this one-to-one. The graph of this one here, because no horizontal line crosses it, it does have an inverse, and its inverse is a function. Here it does not. I think I put that way too high. Yep, there we go. Locked in place. Okay. I think for the most part, finding inverses were good. Linear equations, like we did with 4x, were good. Because it's just switching it, solving for y. Most quadratics that you'll see, and we can cover some of these, especially tomorrow if you get stuck on those, please let me know, are not overly terrible. That's still a strange sentence, but they take a few steps. We're not going to get anything in a true quadratic form, as in x squared plus 4x plus 4. Because then there's a lot more steps we have to do to get it into an inverse. And there's ways to do it. I've done it before. I can try to see if I can pull the equation back out. Because I think there is, and there's probably on the web, a inverse quadratic equation that you can plug in the values and it'll give you the inverse. So on and so forth. Because most of those will be 4x squared plus 4. Not too bad in getting it by itself and solving. For x cubed. But this one here is new. Because I don't believe, because I know for Algebra 2 we did not cover this type, finding this inverse. Or at least not in depth. I don't know if you covered a type like this here. Now, the steps are still the same. If I want to find the inverse, the first thing I want to do is rewrite f of x as y. That's first main step. Rewrite f of x as y. Second step is to switch x and y. Now, unlike most of the ones that y'all done before, normally we had 1x, 1y. We just switched it. Here, when we switch it, every x becomes y and every y becomes x. And this is where it gets a little complicated, because what we need to do is to, 1, get rid of the fraction. 2, Once we do that, we need to get the y's together. We need to group them on one side. So the first thing I can do is multiply both sides by the denominator. Now the right-hand side, the 3y plus 2 and 3y plus 2 will cancel, leaving us with 5 minus y. That's nice. Now the left-hand side, we will need to distribute the x. 3y times x is 3xy. 2 times x is going to be plus 2x. And now at this point here, we need to get the y's together and everything else on the other side. So anything that has a y needs to be moved to the same side. So what I can do is add y to both sides. Here, the negative y and positive y will cancel, leaving us with 5. Now over here, we'll have 3xy plus y, because again, x, y, and y are not like terms, so they stay separate. But we also have plus 2x. And again, we need the y's by themselves. So what I'm going to do next is subtract the 2x. I need the 2x on the other side. Because the goal, 5 minus 2x, is to have all the y terms, any term that has a y variable on one side, and any term that doesn't on the other. And this may seem very strange, very weird, especially if you've not seen it before, because there is a goal. And that goal is to get the y's together, but now, if I look at these two terms, do they have a common factor? Well, they have y in common, yes? So what I can do is I can factor that y out, and if I do that, y out of 3xy is just plus 1. Where I started out with an equation, once we switch the x and y, we're at y in multiple spots. I have now got it to a form where I only have it in 1. And that's the goal with these here. Now at this point, to get the y by itself, I can divide both sides by 3x plus 1. These will cancel, telling me y is equal to 5 minus 2x divided by 3x plus 1. Which tells us f inverse of x is equal to 5 minus 2x over 3x plus 1, because it's inverse. And a lot of these here, it's almost easier to quote-unquote verify that they are inverses by finding the inverse of 1 than it is to try to plug them in. But it does work. Because we have that there. 5 minus x. Yeah. Okay. I did not want it to do that. There you go. So we have these two here. Make this easier to work with. Control. Okay. So that should let me, yep. Because I can try, or not try, but we can take the inverses and see f of f inverse of x would be f of 5 minus 2x over 3x plus 1. Which at this point we're saying, okay, I don't see how this is overly complicated. But at this point we've got to plug this in for every x. So we have 5 minus 2x over 3x plus 1 over 3 times 5 minus 2x over 3x plus 1 plus 2. Now the easiest next step, and I'm going to work y'all through this, I'm not going to ask you guys to prove one as difficult as this kind of step through. I don't believe if I do, it's going to most likely be a bonus, and that's going to be it. The first thing I'll need to do to simplify this, or go about simplifying it, is going to be to multiply both sides by the least common denominator, essentially what the denominator is. Because if I multiply this by both, the first part is going to be 5 times 3x plus 1. We'll simplify that here in a minute. But when I multiply by the fraction, the denominators will cancel, giving us just the numerator 5 minus 2x. We put it in parentheses because of the subtraction in front. Now when we do this with the denominator, we still have the 3, but the 3x plus 1 that we multiplied it by in the denominator will cancel, leaving us with 5 minus 2x plus. Then we have 2 times 3x plus 1. Now we're going to do some distributing. So in the numerator, 5 times 3x is 15x. 5 times 1 is 5. If we distribute our negative, we'd have negative 5 plus 2x. In the denominator, we'll distribute the 3. 3 times 5 is 15. 3 times negative 2x is negative 6x. Distribute the 2. 2 times 3x is 6x. 2 times 1 is plus 2. Now in the numerator, 5 minus 5 is 0. The denominator, negative 6x plus 6x is 0. 15x plus 2 is 17x. 15 plus 2 is 17. Lo and behold, we do get x. So it is possible we can do it. But again, I'm not going to make y'all do those because as we can see there, it is a decent process to try to get there. And in some cases, it's almost easier just to find the inverse than it is to figure out if they are, the test, and do the test to see if they are. Questions on any of this here? 5 minus x over 3x plus 2. Clear that out. 5 minus x over 3x plus 2. Yep. 5 minus 2x over 3x plus 1. It is kind of hard to see, but they are indeed inverses of each other. They're kind of flipped across that line. Now it's hard to see, especially the left half, the bottom in quadrant 3 is a little weird like that, but they are indeed inverses. Questions on any of this here? And that's it.